Hello. Why do we even have mathematics? Well, it turns out that from the time of the ancients and through until about Newton, one of the principal drivers for the development of mathematics beyond basic arithmetic was astronomy. And almost all the mathematicians you've heard of from that era were also astronomers. And some of them would have thought of themselves as primary astronomers. So in this short sequence of videos, I'm going to look at the mathematics involved in how we eventually answer the question of how far away the sun is. So here's my title. The three videos. The first one, we're going to look at how far the ancient Greeks got, which was to get a pretty good estimate of how far away the moon is, and a pretty lousy estimate of how far away the sun is. In the third video, we'll look at one of the greatest international scientific projects ever that eventually got us a good answer to how far away the sun is. And in the middle video, we'll look at the scientific advances that enabled that great project to succeed. But we start with the Greeks. And this guy, who you may not have heard of, he's one of the earliest of the ancient Greeks. Really, only Pythagoras of the famous ones is before him. Of course, we've no idea what he looked like, and this is something drawn 2,000 years after he died, and some odd. It's actually a fresco, so it's not a drawing. Well, we know it's not right because he would certainly not have been pointing at a globe, whatever else he might have been doing, because he believed the Earth was flat, which is not a good start on a journey, is it? However, the other things he did were so he was actually born in what's now Turkey on the east on the western coast of what's now Turkey, but he moved to Athens. Um, and he was the first one to realize that the moon shines by reflecting sunlight. That's a big step. And he also gave the correct explanation for eclipses, namely that an eclipse of the moon happens when the moon falls into the shadow of the earth, and an eclipse of the sun happens when the moon comes between the earth and the sun. So those are two important steps. And of course, in particular, that means that the sun is further away than the moon. Right, so that's a step on the road. Okay. So the next step is to get rid of this nonsense about the earth being flat. And this is the guy who is credited with first giving a really convincing argument that the earth is roughly spherical. And we do know a bit what he looks like because this is actually a Roman copy, an ancient Roman copy of a Greek statue of Aristotle made in his lifetime. So he probably did really look a bit like that. Not this cloaky thing, that's a much later edition, but his actual face. That is probably what he looked like, roughly. So, of course, famously, he was born in Macedonia in northern Greece, but he spent a long time in Athens, 20 years in Plato's Academy, where he founded a great library. And of course, he became tutor to the future Alexander the Great. Philip of Macedonia summoned him back to Macedonia to become tutor to his son, the future Alexander the Great. He'll appear in the story later as well. Okay, so his argument about the Earth being spherical. Well, first of all, it's obviously now flat because you can see ships sailing over the horizon. So that was always a daft idea. People thought people had thought it was spherical before, going all the way back to Pythagoras, but the convincing argument here is Aristotle's, and it was based on lunar eclipses. So let's look at some lunar eclipses. Here's a whole bunch of them. Now, what do you notice? Well, these are all pictures taken before the eclipse becomes total and the moon disappears altogether. And so what you can see is the edge of the shadow of the Earth falling on the moon. And you should notice it's always roughly circular. There it goes. Whether you're seeing a shadow of, as it were, the top of the Earth or the bottom of the Earth or the left-hand side or the right-hand side and whatever attitude the Earth's in, you always get a circular shadow, edge to the shadow. And so that really shows you that the Earth is spherical. No other way, no other shape that can do that. So the edge of the shadow is always circular. It's important to realize that this doesn't tell you anything about the shape of the moon. It is the Earth we're looking at here, because here's a shadow of a photographer with the light behind him cast on something which isn't anything like a flat piece of paper. It's a rumpled old shape of a cliff. And if somebody looked at that shadow from the side, they wouldn't necessarily see a very clear picture of the person. But the person himself, with the sun behind him, sees a good image of himself. And that's what we're seeing with an eclipse of the moon. We're seeing a good picture of the Earth, and it tells us nothing about the moon. By the way, those pictures of the eclipses look a bit like phases of the moon, don't they? So part of the moon lit and part not lit. But of course, this is actually a completely different phenomenon. Here we're looking at the moon, as it were, from the side and looking at the sunlit side and the dark side. Um, and that, incidentally, tells us that the moon is round, is roughly spherical, because you wouldn't get that effect if the moon were, say, a disk. I mean, if it were a disk always looking at us, sort of going around like this, then you'd either see the whole circle if you're looking at the sunlit side, or you'd see none of it. And if it was sort of going around like this, always facing the sun or something like that, then again, you wouldn't see this sort of effect. You'd see actually symmetrical elliptical shapes. So what we actually see is pretty good proof that the moon is roughly spherical. But returning to here, what we're seeing is that the edge of the shadow of the Earth is always circular, and therefore the Earth is round, spherical roughly. Okay, well, logically, the next step is actually to find out how big the Earth is, but that comes later chronologically. The next step is this very famous guy, Aristarchus, a little bit later, but still well BC. He was also born on west coast of Turkey. Probably most of his life in Alexandria, because by now, of course, Alexander the Great has grown up and conquered the world, and in particular founded Alexandria, which is rapidly becoming the sort of intellectual world capital of the Greek-speaking world. Okay, so now his contribution was to find out how far away the moon is in terms of the size of the Earth, which he didn't know. That's quite clever and abstract thinking, isn't it? And it works like this. It works on eclipses of the moon again. So let's suppose for the moment, as a simplifying assumption, that the shadow of the Earth is just a long tube of darkness. It isn't, but we'll come back to that. Let's get the idea right. So an eclipse of the moon happens here when the moon disappears into this tube and comes out again. So well, I've drawn here the point where it just first starts to disappear, and down here where it first just begins. So the distance it moves from here to here is the diameter of the Earth. And the time it takes is about 2.5 hours to do that for a lunar eclipse. And so we can work out this, and we know how long it takes to go right round, which is 28 days. So the circumference of the moon's orbit, the whole distance right round, divided by the diameter of the Earth, that's this little bit, is equal to 28 days divided by 2.5 hours. So that's about 257. And if you work that out, it means the distance to the moon is about 80 Earth radii. Now, that's not right, of course, because Earth's shadow isn't a tube. Aristarchus did better than that. And his next step was to try and estimate the ratio of the distance of the sun to the distance to the moon. And that's pretty clever stuff. And for this, he used phases of the moon, and in particular, the half moon. So, half moon, I don't think we did realize this, doesn't come halfway between the full moon and the new moon. It comes when this angle here is the right angle. This is the Earth, that's the moon, this is the sun. So we've got the sunlit side of the moon, and we're looking directly along that edge, as it were. So exactly half of the moon is lit, and that means that angle is a right angle. So halfway between new moon and full moon would be here, wouldn't it, where this angle is a right angle. It's not that. So Aristarchus reckoned he could work out this angle beta. And if he could do that, then the distance of the moon divided by the distance of the sun is what we would call the cosine of beta. That's a little bit of trigonometry. Trigonometry hadn't been invented yet, and that didn't daunt him. So he invented a little bit. He estimated beta to be 87 degrees, whereas in reality it's 89.5 degrees. And he worked out what we'd call the cosine of beta, and it's 1/19. So he reckoned that the moon was 19 times, the sun was 19 times further away than the moon. Now, this was a hopelessly optimistic idea, really, because in order to do this accurately, you've got to estimate with your naked eye looking at the moon when this exact half moon happens to within, much less than an hour, a few minutes. And that's obviously impossible. So there's no way he was going to achieve that, really. But it's still a good idea. And at least it did show that the sun is not just further away than the moon, it's a lot further away than the moon. And this is actually the book he wrote about all this. It's rather interesting. This is actually a 10th century copy. And here's his picture. So now he's got the sun and the earth and the moon traveling through the shadow. Pretty good, isn't it? Here are his results. So in terms of the radius of the earth, He reckoned that the moon's distance was 20 away, but actually it's 60. But he made a sort of schoolboy error in this because he got the easiest bit of the calculation wrong, which is the angular size of the moon, which is half a degree. Same for the sun, of course. The apparent size of the sun, if you look at it, it's half a degree. Um, and he made the error of using a different value. And that's a bit silly. He didn't measure it himself. He looked it up in other people's books. And I think there was a misunderstanding about the unit of angle being used because the degree had not yet become the standard unit of angle of measurement. Euclid, for example, uses the right angle as his basic unit of angle. Anyway, he made a mess of that and he got the wrong answer, but well, that's not bad. But he did more than that. So he then said, oh, wait a minute now. Um, the sun is so much further away than the moon that it's a lot bigger than the moon, and in fact, a lot bigger than the Earth. So much bigger that surely the Earth must be going around the sun, not the sun going around the Earth. Well, that's interesting, isn't it? Um, Now, people didn't accept that argument, and not as it's sometimes said because they thought it was heretical or, just they were too conservative. No, they rejected it for a good scientific reason, which is, and if that were true, then the night sky would look different in spring and in autumn, as it were. You're looking at it from a different angle, and so it would look different, and we don't see that, and so this can't be true. Well, spoiler alert, the Earth does go around the sun, and the night sky does look different in spring and autumn. But the difference is so absolutely minuscule that nobody could possibly notice it with a naked eye. And that's because the stars are so much further away than the sun than anybody could conceivably imagine. They had this sort of model of, the moon going around the sun, going around the Earth, and then the sun somewhat further away, and the other planets, and then the stars a bit further than that. And in fact, the stars are sort of 250,000 times further away than the sun, and nobody could imagine that. So that idea didn't last. So the next step was actually to find how big the Earth is, and that comes to this guy, Eratosthenes. So he was born in Africa, actually, what we now call Africa, um, in a Greek city, and he studied at Plato's Academy, like Aristotle, and he eventually became the librarian at Alexandria's famous library. And he measured the Earth, and he did it this way. So he heard tell that in Syene, which is further down the Nile, further south along the Nile, there was a well where if you looked down it at midday on the summer solstice, you could see the sun reflected in the water at the bottom of the well. And he thought that was remarkable. But more than that, he said, aha, what that means is that the sun is vertically overhead at midday on the summer solstice in Syene. And he said, well, okay, so what's the angle of the sun in Alexandria, where I live? And he worked out it was 7 degrees. And so he could draw this picture and say, oh, well, this is 7 degrees here. And that means this little arc divided by the whole circumference of the Earth is 7 divided by 360. Um, so, and he knew the distance of Alexander to Syene, or he found it out, um, as 5,000 stadia, as measured by Bemetis. So this is where Alexander the Great comes in again, because there were these people called Bemetis whose job it was to walk along measuring distances. So presumably they were specially trained to walk a very steady pace and not lose count. And Alexandria took a team of Bemetis with him on his conquering of the world, so that he would know how big his empire was and how far apart all the cities were. And there were Bemetis in Egypt at this time, and they would have either already known, I could easily have found out the distance between Alexandria and Syene. So he got the arc to be 5,000 stadia. That's to say, the length of a stadium. Well, of course, I mean, there are several Greek stadiums around the world, and we don't know which one was used as a standard. So we don't really know how long this unit of length was. But so anyway, he got the circumference to be that, and he ended up with a radius of 40,000 stadia. And we can make a reasonable guess at how big a stadium, and it's about right, actually. So his answer to the size of the Earth was, pretty good. So now we know the size of the Earth, and we know how far away the Moon is now, roughly. And we also know the size of the moon, of course, because we know this half-degree business. And we think we know the size of the sun, too, because there's a ratio of 19, though actually that's completely daft. It's not anything like that. But we're making progress. Okay, so the next guy, he came up with another version of the size of the distance to the moon. This is important for a different reason. So he's called the father of trigonometry because he was the guy who really did invent trigonometry. So Aristarchus had worked out one trigonometric ratio, which is what we'd call the cosine of 87 degrees, and this guy had worked out the lot. His work is not survived, but we know he did it. Um, and he observed a total eclipse, which we can now work out would have been on the 8th of June, 129 BC. And it was total at Nicaea, who actually, again, another place on the west coast of Turkey, but covered only 4/5 of the sun at Alexandria. Now that allows us to estimate the distance to the moon as something like 80 radii of the Earth. And this relies on the idea of parallax. So let me explain parallax because this is going to happen again and again. We're going to use a lot of this idea of parallax. Here we are. Here are 2 points on the surface of the Earth, and this is the moon or some other distant object. We know this distance, let us say. If we knew this little tiny angle here, we could work out this triangle, couldn't we? And we could work out how far away this. It wouldn't matter if this one quite a right angle. It'll do. So how are we going to work out the little angle? Well, we can't go to the moon and measure it. And it's no good measuring this angle and that angle and adding them up and subtracting from 180 because this angle is very, very tiny. So these angles are both, their sum is very close to 180. And we can't measure them frightfully accurately, especially if these points are a long way apart on a spherical Earth. It's really hard. And if we worked them out very roughly and added them and then the answer is very close to 180. Subtract that from 180 and you've got no accuracy left at all. It's a hopeless idea. So what you do is you look beyond the moon and try and measure this angle, which of course is equal to that angle. And to do that, you need a sort of protractor in the sky. And for this purpose, we use the sun. So what we have here is that from this point here, the shadow of the moon is right at the bottom. The bottom limb of the shadow of the moon is coincident with the bottom limb of the sun because it's a total eclipse. But from this perspective, it's a fifth of the way up the sun. So this angle here is a fifth of the angular size of the sun, which, like the moon, is half a degree. So that's a tenth of a degree. So this angle is a tenth of a degree. And so we know this distance. It's clever, isn't it? So now we've got two versions of the distance to the moon. We have Aristarchus's, which was about 20 and was completely wrong because he got the... So if he'd done it right, he'd have got something more like 40. And Hipparchus got something like 80 and the right answer 60. So actually that's not bad at all, is it? And by the way, the modern measurement of the moon's orbit and the distance is this little thing here, which is the cube corner reflector, which allows you to shine a laser off the moon and measure the time it takes for light to get to the moon and back. And so we can now, that was left there by the Apollo guys. So now we know the distance to the moon to within a millimeter. Okay, so that's the end of that video. Next time we'll be looking at these greats of the scientists, greats of the scientific revolution, as it's called, ending up with Newton, at the end of which time we've got a really good map of how the solar system works. So I'll see you then.